Hi all, welcome to today's DSL Go class. In today's session, we are going to solve the problem called unique paths 2. So this is similar to what we have seen earlier, which is unique paths 1. Just there is one additional constraint over here, that there could be some of the squares which are having obstacles. So whenever there is any obstacle, you cannot pass through that obstacle. Okay, so let's jump right into the problem. So similar to the problem that we have seen before, we have to start from the top left corner and reach to the bottom right corner, and there will be some obstacles. Now how will you identify the obstacles from the input array? Is wherever you see one, right, that means there is an obstacle. Hence I have marked this one to point to the obstacle. Now, like before, we'll also take the similar approach. We'll try to build the base cases first. We'll put all those base cases together to form the final solution. So, if you haven't seen the previous video, I would request you to go and check it quickly so that it will form a good basis for this problem. Now, if we see over here, we will return 1. In which cases? When your I and j, okay, so this is your I and this is your j. When your I and j is equal to m minus 1 and n minus 1. Okay, now what is m minus 1 and n minus 1? It is the number of rows in the grid and number of columns in the grid. So m stands for rows and n stands for columns. Okay, now what will happen if we face any obstacle? So in that case, we will return 0. Okay, so if so far things are clear to you, let's go to more generic cases. So as we have seen over here in this part, if we have reached the final cell, that means we have to return 1. Okay, so let's consider this general example wherein we are considering just one row, whereas number of rows are 1 and number of columns are 4. So you can see clearly over here, the star stands for the last cell. Hence one possibility is there, one unique path is there, which will reach us to the help us reach to the last cell. Okay, now what will happen next? Imagine that let's do some imagination over here. So assume that whatever is highlighted in green is not revealed yet. Okay, so we'll try to grow the problem step by step. So imagine that only one cell is given to you. So in that case, we have seen that there is only one option over here. Okay, now imagine that another cell is revealed to you. Now how many options will we have from this cell to this cell? How many unique paths can we draw? Okay, so the answer is 1. Why 1? Because answer of this cell is actually dependent on this cell, and since this cell is 1, we can say this will also be a 1. If things are clear so far, we can move on to the next part. In this case, we will actually unveil another cell. So imagine now the problem is you have one row and 3 columns. Okay, so what will happen in this case? We can say there is only one path that starts at this cell and ends at this cell. Now how is this possible? Because we know at the end cell we have only one option, the cell previous to that we have only one option, and hence we are saying that here also we have one option. So if you can imagine, this is actually forming a recurrency relation, which is an intuition to you saying that probably we need to use recursion in this case. Okay, similarly if I unveil this cell as well, so the problem is now grown to one row and multiple columns. So in that case, as we know, here we have one option, here we have one option, here we have one option, similarly here we have one option. So from this cell to the end cell we have only one unique path. Okay, if this makes sense to you, we will now consider the similar example only with the columns. Okay, so we are going to talk about this part. So imagine that only this much problem is revealed to you. Okay, only this much problem is revealed to you. So we know if we are already standing at the end cell, that means we have only one option. Now I will reveal another cell to you. Okay, so now we also know if this is 1, if this is 1, this value has to be 1. Why? Because this solution is actually dependent on the solution to the next cell, okay, which we have already computed over here. Similarly, if I reveal the next set, we will see that 1 is over here, and similarly 1 will come over here. And again, re-emphasizing on the same point that this is sort of a recurrence relation, because whatever we have found earlier will contribute to the next solution, and hence this could be solved by the recurrence relation. Okay, we will be using recurrence in this case. Now let's say we take more complicated example. So let's assume we have taken this particular example. So as we have discussed, the last cell will always have answer as 1. Okay, the cell above it will be dependent on the output that we have found earlier. So in this case, this particular output, okay, it is dependent on this. Similarly, this cell's value will also be dependent on this, and to make these assumptions, we have already clarified that this is when it comes to rows, we have to follow this pattern, and when it comes to columns, we have to follow this pattern. And this particular problem is combination of both. So here we can see there is a column, and here we can see there is a row. Okay, but now what will happen to this cell? Okay, what should be the value of this cell? So as you can see, there could be one path that is going from here to here. Okay, and there could be another unique path that is starting from here going till here. Okay, so this emphasizes that value of any cell I j will be dependent on two factors: the value of right cell and the value of down cell. Okay, so if this part is clear to you, let's try to generalize the overall case further. So imagine the square which is put over here, the square, the black square which is inside the red square, is actually your problem statement. Okay, and whatever is colored in red color is essentially something which is out of bounds. So what does this indicate? What does this particular part indicates is anything that is out of bounds is treated as 0. Okay, so this is very important, guys. So whatever is out of bounds, we have to treat it as 0. Now so far, if you have understood these all base cases, the recurrence relation is very simple. We have to put all these base cases together to form a final solution. So here my recurrence function will start. It will accept I and j. Now what is I and j? So we have to find the unique paths that lead to the final cell from the starting cell. So for here we will put whenever we'll call the recurrence function, we will put 0 and 0 over here. Okay, m is number of rows as we have discussed, n is number of columns as we have discussed, and grid is actual problem grid which we have been given in the question section. Okay, so as we have discussed in the first part, okay, over here whenever we reach the final cell we will return 1. Okay, so that is what I have written over here. Next, for any valid cell, now what does the valid cell means? As we have discussed in this part, okay, anything that is out of bounds should be treated as 0, should return 0. So if any cell is invalid, okay, so for example, if number of rows is 3 and false is 2, then any value of I and j that goes greater than equal to 3 and any j that goes greater than equal to 2 are actually invalid cases. Okay, hence we are returning 0 over here. Now what will happen if there is any obstacle? So we have studied this part over here, correct? So I'm putting that constraint over here, that whenever you see an obstacle, return 0. Now moving ahead, as you can imagine over here, we will be computing few values again and again. So for example, if there is a grid like this, okay, with multiple rows and multiple columns, then we may find one path going like this, other path going like this, other path going like this. So if you see over here, we have computed this value more than once, okay, and hence the recurrence will be costly affair in this case. And now we have to optimize it further using dynamic programming. So the part of dynamic programming is mentioned over here. Okay, this is your DP. So in case of Java, if you have say integer 2D array of integer type, then any value, so what all values can this hold is null or any value, okay, that is inside the integer boundaries. So what I am checking over here, that for this particular cell, okay, for this particular cell, if I have computed it already, that means it is not null, then I have to return it. Okay, and again as we discussed in over here, okay, whatever value of this particular cell is actually dependent on the next cell, next as in the cell on the right, and cell which is down. Okay, so how will we identify right cell? So we will have I similar, but j will increment by 1. And how will we identify the down cell? We will simply increment I over here and j will remain as is. So these two states are actually your taking care of your core logic, which is computing the response of right and down. Okay, if this part is clear to you, you can easily understand that since we are passing on 0 and 0 over here as the base input, the final answer of unique paths will be found over here, right, in this case, in this grid, and hence we have to return dp of ij. Now if you are clear with this explanation, here is the code that I have implemented. In this case I have a isValid method. Okay, isValid method is very simple, it just checks for the boundaries. Okay, in this is valid method, we are checking the boundary. Okay, boundary condition over here. Okay, and then we are checking if the grids I and jth element is not 1. Why 1? Because 1 indicates obstacle. Okay, and we don't want to fall into obstacle cell, hence we are also checking if there is obstacle or not. If the I and j is within boundaries, okay, if I and j is within boundaries, as well as there is no obstacle seen on the ij row and column combination, then we will say that this ij combination is indeed valid, and if it is valid, then only we will move ahead to the later part of the recurrence relation. Okay, so this is the code for you, and thank you so much for watching.